Okay.
Let us, yes, it is full screen.
Okay, thank you. Thank you very much. So, the title of the work which I'm going to present here is like I just want to give some properties and applications of the two-dimensional q-Bessel polynomials, and I think that it is quite appropriate to talk about the q special functions or q-Bessel polynomials after a talk of Professor Srinivasa Rao on the relation of quantum algebras with special functions. So this is like first, I would like to give a brief abstract and, of course, the motivation behind the work which we have done here. Then some introduction and preliminaries about the Q calculus, some concepts which are a bit new to the persons who are working with the special functions. And then we will go for the main contents of this work, that is generalized two-dimensional q-Bessel polynomials. We'll take some examples, and also we would throw some light on how they look. So we'll consider the graphical representation as well. So we all know that this has witnessed a significant evolution during the recent years due to its applications in various fields such as mathematics, physics, mechanics, and engineering. And the Q calculus has drawn attention of many researchers in the field of special functions because we notice that it serves as a powerful tool to do the modeling or to model the quantum computing. And as a result, I think there are like there is a one-to-one correspondence between special functions and their Q analogs. So the result, the Q analogs of certain special functions are introduced and studied. And here in this work, we introduce a generalized two-dimensional extension of the q-Bessel polynomials. Q-Bessel functions were introduced, but we try to take a q-Bessel polynomials and then we try to introduce a two-dimensional extension of this. And we do this with the help of generating function and series definition, because I feel that these two expressions help us in achieving so many properties. In fact, most of the properties related to that particular special function or q special function. Interestingly, or in addition or as a bonus, we'll also do some properties like determinant expressions, recurrence relations, of course, the q recurrence relations, and q differential relations also. And then we consider some examples to show that how efficient or to show the efficacy of the method we are proposing in this article. And finally, as I mentioned, that we will be going to see how these polynomials look with, of course, some specified values of q and some specific values of the indices involved in the polynomials. And the contents of this talk are based on my recent research work with my students, Mumtaz Riasat and Mehnaz Hanif. Mumtaz Riasat is currently working as a contextual faculty at Department of Applied Mathematics, and Mehnaz Hanif is enrolled currently under my supervision. And this paper we have communicated to reports on mathematical physics, and we keep our hand like fingers crossed that I hope it will get accepted soon. And then Dilip, it is not changing the slide. Okay. Okay. Okay.
Yes, it is not
Yes,
changing.
now it's fine. So now we review certain definitions and concepts of Q calculus. This is the book which we followed for the concepts related to the Q calculus. Andrews, Askey, and Roy, published by Cambridge University. So these are the concepts I think most of us know about the Q form of a complex number beta. It is, we take for 0 it to be 1, and this is the specific notation, and then for n we take these the product of 1 minus q power m beta factors from 0 to n minus 1. uh, obviously beta and q we are taking to be real numbers, and n belonging to the set of natural numbers. And this symbol, Poisson symbol for beta, is defined as 1 minus q power beta upon 1 minus q. And here we restrict q to be belonging to C except the set containing 1, that is, it should not be 1. And beta is also belonging to C. The factorial of q, q factorial, we can consider it in this form, that is summation m equal to 1 to n, the product of the factors 1q, 2q, and q. And we also can also express it in this form, that is the qqn, here we have defined, and 1 minus q power n. Q we are restricting not to be equal to 1, and n is n. And as in the normal factorial, we have the q factorial q 0 of factorial 0 q as also 1. So also, we take the q analogues of the exponential functions. Now we are using two types of exponential functions, one with a small and one with capital E. So this is defined as u power n upon n q factorial, and this we have additional q power n minus 1 by 2 in the q exponential with the capital E. And again, we restrict mod q to be greater than 0 and less than 1, and u is in the complex set. Now, it should be noted that this exponential, q exponential with capital E is analytic in the whole complex plane, whereas this q exponential with the small e is analytic in the complex domain, that is the inside of the disk module less than 1. And there are some interesting relations between these two exponentials. If we take a small exponential with u and capital with minus u, this is 1. And also, if we change the roles of u, then this is also equal to 1. Regarding the derivative of the small q exponential with small e as the same, and with capital E, it will come out as here u will be replaced by qu. And now, if you want to know about the q derivative of the function h, if for arbitrary function h, we consider the q derivative, it is defined in this way, that is h of qz minus hz upon qz minus z. Again, the restriction on q is that mod q greater than 0 and less than 1. And also, this is the product formula that we will be going to use whenever we encounter with such type of situations, that is, the q derivative of the product of two functions will be hqu, dqgu, and then gu, and then dqhu. Quite similar to the formula for the ordinary derivative for the product of two functions. Now, we all know that Bessel polynomials satisfy the orthogonality property, and whenever we find some polynomials or functions with orthogonality property, our interest in this, it attracted us because of the fact that it increases its applications in physics. Okay, so it have applications in mathematical physics problem. Recently, we have published a paper in Daxam, which is related to the determinant approach to q-Bessel polynomials and applications. And in this paper, we have considered this q-Bessel polynomial of single variable u, with the generating function is written in terms of the q exponential with small e. And also we have expressed, I'm trying to consider the generating function and the series expansion most of the times. So this is having this explicit series expression, this q-Bessel polynomials. And also we consider another form of q-Bessel polynomials, which we have which is slightly different from the P and QU polynomial, and it is related to this polynomial by this relation, that is theta and QU is 1 upon U P n plus 1 QU. And these polynomials, the second form of, I should say, q-Bessel polynomials are defined by this generating equation. That is, we have an extra expression 1 upon under root 1 minus 2 alpha also here. And here we will be having alpha power n upon n cube factorial. So moving ahead, And also we will be writing the series expression for the second form of the q-Bessel polynomials also, which is related to Pn plus 1 Qu and of course divided by u. And this is the explicit series form for the second form of the q-Bessel polynomials. So here what we are going to do is, actually there is a two variable polynomials which we call in that paper as two variable general polynomials, but it was published that time and I don't remember, but someone told me that you should not call it general. I think Professor A.K. Agarwal. So now I'm calling it generalized two variable polynomials P and UV. And this is the this is the reference. I think this is not mentioned properly here. This is another paper, so I'll show you in the list of references. Now for q belongs to C and mod q greater than 0 and less than 1, the generalized two-dimensional q polynomial. So this is where we are starting now. That is, we are taking the two-dimensional q polynomial. So we have taken the two variables here, n is the index and q is for q polynomials. And here we have this q exponential with small e, and this function phi q nu alpha, which is having this series expression. Analytic expressions are in summation n running 0 to infinity, find qv alpha n upon nq. And of course, we are restricting this function that for n equal to 0, it should not be, it should be non-zero, it should not be 0. So for different choices for this function, like you have in the case of Apple functions AT, we choose different type of AT. So here this function, if we choose in different ways or for some suitable choices, I should say, then we will be getting some members of the generalized two-dimensional q polynomials family. So as some of the members I tried to mention here, that is continuous two-dimensional q Hermite polynomials with the choice of this function in this form, that is the exponential with capital Q exponential with capital E, and then this thing, and with the specified generating function in this form. Both types of q exponentials are occurring here, and this is the notation for the continuous 2D q Hermite polynomials. Then we have two-dimensional q Bernoulli polynomials with this generating function, and of course the choice for phi q nu alpha is this, like this. And then we also have two-dimensional Rogers Sacco polynomials with the choice as the product of two q exponentials, capital EQ as nu alpha and small q exponential with alpha only. And this is the specified generating relation for 2D Rogers-Sago polynomials. Then we also have 2D Al-Salam-Khalid polynomials. These polynomials are quite important, and here we have introduced their two-dimensional analog, and of course the q two-dimensional q and q Al-Salam-Khalid polynomials. So this is also q here missing, and here also we are having two-dimensional q Al-Salam-Khalid polynomials. So I think we have enough works on q-Bessel polynomials to motivate us to introduce a general class of the two-dimensional q-Bessel polynomial. So we are introducing it here, and also we will be going for its determinant form, because we feel that the determinant form opens possibilities to deal with the polynomials in like wide. It increases their applicability, and it make them more. It makes like applicability more wider. And we will be going to consider an example by taking a particular member of this generalized class. So, generalized two-dimensional q-Bessel polynomials, how we are going to introduce? We are we will be going to consider this q exponential with a small u, small e in the left hand side of generating function of q-Bessel polynomial. So we are starting the base polynomial, that is q-Bessel polynomials. And then we will be replacing the powers of u appearing in the expansion of this q exponential, that is u naught, u1, u2, un, etc. by the q polynomials. Now these q polynomials, that is the two-dimensional q polynomials. So these are g0 q uv, g1 q uv, and so on. in the same equation. And then when we take the when we do the sum, or we take the sum of the terms, then in the left hand side we'll find this type of expression. And here, because we have replaced, here we are having x, okay, sorry, u. So the power of u power 1, u means u power 1, so that we will be replaced by g1q uv. So here we have like this. So then we can make use of the generating equation of the generalized two-dimensional Q polynomials, which we have taken in the previous slide in the left-hand side, and then we are adopting this type of notation for the generalized two-dimensional q-Bessel polynomials. That is, if we are taking the two variable, if we are taking this q-Bessel polynomials and we are replacing the u's or the powers of this by the q-Bessel polynomials, then we will be getting the following definition of the generalized two-dimensional q-Bessel polynomials. The notation we have used as G, P, and Q, U, V. And this here we are. Now you can notice that in this generating equation, we have this q exponential with a small e, and then this function, okay? And this function is now we have defined by find qv, and then here we have 1 minus under root 1 minus 2 alpha power n upon nq. And for the generalized two-dimensional q-Bessel polynomials, we, as I mentioned earlier also, that we will be going to consider the series expansion also. So this is the series expansion for the generalized two-dimensional q-Bessel polynomials. It is in terms of two-variable general polynomials. So if you use the series form for this, then we may get the explicit form involving the two summations here. So that can be done very easily. So the generating function and series expansion, I forgot, we have considered another form also of the q-Bessel polynomials, which we have denoted by theta and q. So corresponding to this, we will be going to have the generalized two-dimensional q-Bessel polynomials in which we are denoting by g, theta, and q, u, v here. Now instead of p, we have theta. And this is the generating function. Here we have 1 upon under root 1 minus 2 alpha, then the q exponential with a small e, and then this function psi q. And also this is because we have related the another form of q-Bessel polynomial, which we have denoted by theta, to the p and q type of polynomial. So correspondingly, or we will be having the analogous relation of this generalized two-dimensional q-Bessel polynomials with the that form of the generalized q-Bessel polynomials. And this is the series expansion. Again, we are writing this expansion in terms of this two variable generalized q-Bessel q polynomials. But if whenever you expand it by in terms of the series, you will be getting an explicit expression. Of course, then there will be two series we have to consider here. And now we'll be moving for the algebraic or determinant approach. So as I mentioned earlier, that this approach provides a unifying theory for all classes of the polynomials and their generalization. And when we consider the determinant theory, then we can notice that this theory is simpler than the classical analytical approaches based on the method of generating functions. So although I cannot agree much with this sentence, but anyhow, because when we express anything in terms of the determinant, of course it increases its scope and it makes it more wider and of course more simple. But there are certain aspects which we can deal or which we can do with the generating function. I'm in a lecture. Okay, so this is the determinant expression for the generalized two-dimensional q-Bessel polynomials. That is, if you see, there is one thing interesting. When we are writing the determinant form for the generalized two-dimensional q-Bessel polynomials, we are not taking u and v here. Rather, we are taking 1 upon u and 1 upon v. Okay, and here it is minus 1 power n, and then the product of these type of factors, and then this determinant, that is with rows, first row as 1 g1 qu gn minus 1 quv, that is in terms of the two variable q polynomial, and then the remaining rows are involving these coefficients. So of course we need to specify these coefficients. So these coefficients are given by in terms of these factorials notation, that is 2 power n q factorial and 2nq factorial. And when you take ijqw minus power minus 1, then this is given by all these type of expression. And here this is the simple expression for these coefficients. Okay, and of course, I and j we are taking to be from 0, 1, 2, and so on, and there is a relation between I and j, that is I should be greater than j, that we have to specify here. Now, as I mentioned that without generating relation, it is difficult to get the things. So we will be going to use the generating relation of the of this second form of the two-dimensional generalized q-Bessel polynomials. We find the determinant expression for this form also. So here we have taken one q-Bessel polynomial with the small p notation, and the another one with theta, and corresponding to both we have introduced the two-dimensional generalized two-dimensional q-Bessel polynomials, and there are three things we are using here, and the third one is two variable generalized q polynomials. Okay, so this is the determinant form for this form of two-dimensional generalized q polynomials. Again, the first row is involving the polynomials, two variable q polynomials. Okay, and I think I just want to know what is the difference. This row is same as the previous one, and the coefficients are same as in equation 24. So what is the difference between this? Here we have these polynomials g and q uv, and here we have these type of coefficients, and here we have this type of expressions. Okay, so this thing is different. Now, as in most of the cases, whenever we take the limit q tends to 1 of the q special polynomials, we'll get to the, or will reach to the corresponding special polynomial. So here also it will happen, that is, if we take q tends to 1 of this two-dimensional q generalized q-Bessel polynomials, we'll be going to get the generalized two-dimensional polynomials. Okay, so this is this G, P, and UV, which is the case when we take the limit q tends to 1. This forms a class of the generalized two-dimensional Bessel polynomials. Okay, the corresponding results for these polynomials. So here you can see this is also a new polynomial here without q. So we have established the results for the two-dimensional generalized q-Bessel polynomials. So whenever you take the limit q tends to 1 in the results of these polynomials, you will be getting the results for the generalized two-dimensional Bessel polynomials. Okay, so the corresponding results for these polynomials are obtained by taking the limit q tends to 1 in the results of the generalized two-dimensional q-Bessel polynomials. Now, as I promised that we will be going to take an example also. So for considering the example, we choose this function psi cube b 1 minus under root 1 minus 2 alpha of the continuous q Hermite polynomial. So we are taking this corresponding to the continuous q Hermite polynomials, and that we do in the generating function of the polynomial which we have introduced, that is the generalized 2D q-Bessel polynomials. So that means we are taking psi q v 1 minus under root 1 minus 2 alpha as this. This is the psi q for the continuous q Hermite polynomials. You can refer the table which I have shown in, I think, sixth or seventh slide. So if we do so, we will be going to obtain, we will be taking this in the generating function of the polynomial which we have introduced. Then we will be getting the continuous two-dimensional q Hermite Bessel polynomial. So now here we have got a specific type of the generalized, or I should say a member of the generalized two-dimensional q-Bessel polynomial family, and that is two-dimensional q-Hermite Bessel polynomials. So one thing I want to emphasize here is that although we are calling it as generalized two-dimensional q-Bessel polynomials, but it is basically a family, because whenever you choose this psi-q according to the member belonging to the two variable q polynomial, you will be getting a different member belonging to this family. So here we have taken one example, and that is giving us the continuous 2D q Hermite Bessel polynomial, and the notation we use is h, p, and s, as we have taken in the suffix p and q, u, v. And this is the form which we are getting for this particular polynomial or particular member, that is the q exponential with a small u, small e, and then again q exponential with capital E, and then again this all expression with a small q exponential with a small e, and this is the notation for the continuous 2D q Hermite Bessel polynomials. So this is one of the members. So now we may get some more properties, and we can throw some more lights on this particular member. So as if we want to get the explicit series expansion for the continuous 2D q Hermite Bessel polynomials, so you can see I was mentioning it in previous slides. So you just open everything in the form of a series and make some simplification, and that definition we are getting as the summation, three summations involving here, and all these expressions involving the factorials and the powers of q and all such type of things, without any polynomial involved in the right hand side. So we have opened all the polynomials, and because now we have a specific member here, so it's possible for us to open it. Now we have the another results, that is we can have the following summation formulae for these. So I think they are the implicit summation formulae, because it is having this 2D continuous 2D q continuous 2D q Hermite polynomial, and here also we are involving having the same polynomial, and this we are having the q-Bessel polynomial. And this is another one for the continuous 2D q Hermite Bessel polynomial in terms of p, k, q, u, v. This has become the second variable, and this is of first one variable. Here the variable is missing before full stop. This is not in the number, this is the variable here. Okay. So now we have the q differential recurrence relations also for this particular member of the two-dimensional q generalized Bessel polynomials, which we call as 2D q Hermite Bessel polynomial. So we get these with the help of the differentiation, q differentiation, and also using the formulae for the product of what should we do for when we get the product of two q polynomials, then which formula, all these things I have mentioned in the introduction and preliminaries. So with the help of all those formulae, we are able to drive this recurrence relation. So you can see that it is making it n minus k. So we can get it with k for k equal to 1 also. And here it is again, when we differentiate it with respect to v, we are considering the differentiation with respect to u, v, and with respect to the parameter s. So here you can see that this one is looking like pure reconciliation sort, but here we have differentiated with respect to the parameter of this polynomial. And then we will be considering certain members of the generalized two-dimensional q-Bessel polynomials family. I have given you one example. So again, if we choose other, we take other suitable choices for this function, then we will be automatically going to get new polynomials belonging to the generalized 2D q-Bessel family. As I mentioned, that this is just not one polynomial, this is a family of the polynomials. So whenever you choose this psi q suitably, then we will be getting the new polynomials, of course, q polynomials belonging to the generalized two-dimensional q-Bessel family, and we mentioned three of them here as two-dimensional q Bernoulli-Bessel polynomials. With the choice for this, if we take it in this form, and this is the specified generating function for the two-dimensional q Bernoulli-Bessel polynomials. And the next one is two-dimensional Rogers-Sago Bessel polynomials. For this, we choose this function in this form, the product of two q exponentials. One with a small e and the other with capital E. And then this is the specified type of generating function. And then we have also two-dimensional Al-Salam Correlates Bessel polynomials. If we choose it in like according to this polynomial. So this is the specified type of generating function here. And again, we can, whatever we have obtained for the generalized two-dimensional q-Bessel family, we can get the analogous results for these particular members. So I have not included these here because they are quite obvious. Just with the help of substitution, we can, and some simplification, we can get those results. And now, finally, I tried to depict the spectral behavior of these continuous two-dimensional Hermite Bessel polynomials. Particular member I have taken, and for this we draw the graphs and surface plots for taking some even and odd indices just to see the pattern. And whenever we need to draw the graphs, we require the use of the series expansions for these polynomials. So that's why I have mentioned it in this explicit form involving the three series. So we draw the graphs of the continuous two-dimensional Hermite Bessel polynomials, and we have taken odd n, that is, we have chosen it to be 19, and also just try to show for even we have taken 20, and we have given the value of this parameter s at 11 and nu equal to 3. So now when we are doing these substitutions, we have taken we will be reaching to something which is just a polynomial of one variable. So that's why we are getting these type of graphs here. For n19, for this for n20, and for the similar values of s and v. There are several possibilities which can be explored to draw the graph, and here also we try to see where these the zeros of these continuous two-dimensional Hermite Bessel polynomials are situated. So we consider the distribution of zeros of the continuous 2D Hermite Bessel polynomials. That is, we have to solve this equation for 0. Um, we we have not included q here, and here also we have taken odd and equal to 13, and even and we have taken 30, and s 11 and nu 3. So this is the distribution of zeros here. And then we try to show the surface plots also. So for that we need to consider both variables here. So we have taken the even n as 14 and odd n as 17, as we have selected or taken 4. And now we have the two variable, this polynomial is of two variables u and v, both are appearing here. So this is this type of surface plot we are getting for these functions. And now again, if we use the series definition, we can get the surface plots for the continuous two-dimensional q-Hermite Bessel polynomials. And this we draw for odd and equal to 3. And we have taken three values of q, that is 0.1, 0.5, and 0.9. So here we included q also, but we have given specific values of q, and s we have taken to be 11. So these surface plots are presented in these figures. So this is for 11, and then 3, and q for q equal to 0.1. And then the next one is for q equal to 0.5, and for the similar values, and then this one is for 0.9. This is just an illustration, and there are several possibilities it may be explored with the help of MATLAB and Mathematica. So anybody interested can maybe consider some other also. And this is for the shape of the continuous 2D Q Hermite Bessel polynomials. For even n, we have taken even n as 6 for q equal to zero point 0.1 and zero point 0.5, and s we have taken 11, and this is for zero point 0.1 q, and this is for point q equal to zero point 0.5. So I notice very little difference, but there is difference in the shapes of the graphs. These are the differences which I have used Costebile for introducing the determinant expressions, and then the Tuli for introducing the q-Bessel functions, and this for basic references, and Crosswell for Bessel polynomials, and then Kikok, Leske, and Sarto for hypergeometric orthogonal polynomials, and their Q analog, some basic things we have taken from it. Then these are our own papers. Some results on Q Hermite based hybrid polynomials. This is published in Glasnik Mathematica in 2018. This one is the recent one which we have extended in this paper. Not I should not use the word extended, but we have introduced a different polynomial by taking the two variable q-Bessel polynomials. And this is the paper in which we have related the 2D q-Bessel functions with quantum algebra EQ2. So regarding the work which we have presented here, two-dimensional q-Bessel polynomials, we will be considering, or we are exploring the possibilities that with the help of the differential difference relations, q differential difference relations, is it possible for us to relate this two-dimensional q-Bessel polynomials generalized form with some quantum algebra? Because I remember Professor Manocha saying that whenever you just see the q spatial polynomial or q spatial function concept, it is for sure that this is related to quantum. So we are trying to relate this polynomial which we have introduced to some quantum algebra, or some or representation of some quantum algebra. Thank you very much for your kind attention, and again Dr. Dilip for providing me an opportunity to sitting at my home and